All right, well, let's get started. We're going to be heading into a new chapter today. So we're going to be looking at a system of equations that involves two variables. So in the last chapter, we were looking at solving with one variable, and today we will start solving with two variables. This particular section of the material, we are going to keep it as simple as possible, but we can take these ideas and extend them to, say, 3 variables and 3 equations or more, right? And so if you go on to pre-calculus, you get a chance to do that. Okay, so first of all, a system of equations is a set of equations. So we have more than one equation, and the solution that we're looking for is the numbers that satisfy all the equations in the set or in the system. Like I said, we're going to keep this really simple, and we're going to be looking at just 2 linear equations. So if we have a linear equation, that means that our variables are just raised to the first power. So nothing like x squared or no higher exponents. And we are going to have an x and a y. And for each variable, you need one equation to solve. So if I do x and y, 2 variables, I need 2 equations. Okay, so that being said, there are 3 possible solutions that we could get from 2 linear equations, right? So 3 ways that 2 lines could intersect or interact with each other. The first is that we could have 2 lines that intersect. Most of the problems we do will be of this type. And so wherever those 2 lines cross, this point where they meet is their common solution, right? A point that they both share. So the solution is the intersection point. And because it is a point, and we mentioned having 2 variables, the solution is going to look like an x value and a y value. So we need both parts. Okay, if our 2 lines do not intersect, what are the other possibilities? So we could have 2 parallel lines. You probably already know this about parallel lines, but they never touch. I always think of like railroad tracks, right? They run in the same direction, but they don't touch each other. And since they don't touch each other, they don't have any points in common. So in this case, there is no solution. All right, the third possibility is maybe we have 2 different equations, but when we go to graph them, they actually graph to be the same line. So let's pretend we have one line as a solid line and one line as a dotted line, and they're overlapping. Right, so we have overlapping lines. In this case, all the points on one line are also on the other line because they're effectively the same line. So all the points are the solution. So we usually say that we have infinitely many solutions. Okay, and I always like to point out that that doesn't mean that the solution is, say, all real numbers or all the points in 2-dimensional space, right? We are still restricted to being on this line. So it is a lot of solutions, but it's not every point in the universe, okay? There is some terminology that goes along with these 3 options. So I'll just jot that down off the side. You may see that in the textbook or in the online homework. So if I have a solution, it's called a consistent system. So this would be consistent, right? Because I have a solution. The last one here, I have lots of solutions, so that would be consistent. Okay, and the odd man out is the middle one, right? It does not have a solution, so sometimes it's called inconsistent, an inconsistent system. Okay, there's another set of descriptive words for these as well, and that describes the equation. So if I have two separate lines, they're called independent equations, right? So this would be independent. Two different lines there. These would be independent. But because the last one, they overlap to be the same line, these are called dependent. Okay, and so it took me a while to piece this together, but what makes them unique, that's the term that kind of stands out. Actually, let me go ahead and say these are dependent equations. So this makes the third case kind of stand out, right? The two equations overlap, that's different. And then this inconsistent system is the one that stands out. And so you'll see the word inconsistent and the word dependent describing these last two options. Okay, so these are the three types of solutions that we could get, and I want to show you one of each of those. But first, we want to talk also about how we're going to solve to get these solutions. So there are several different methods. One of the methods is a graphing method where we would graph the two lines, maybe more precisely than we just drew on our pictures just a second ago, and we would look for that place where they cross. This is really hard to do on paper because you have to be kind of precise, and so I usually assign you guys a lot of online homework questions that deal with graphing. So you can expect this to come up in the online homework because there's a nice graphing tool that allows you to be really precise, a lot easier than it would be to do it on paper. So I'm going to spend my time going over the other two, which are substitution and elimination. So let's start with substitution. So the idea behind substitution is that we're going to take one of the equations and isolate one of the variables. So I'm going to choose a variable to isolate, either x or y, and I'm going to rearrange the equation and get that variable by itself. And then I'm going to substitute for that variable in the second equation. So for this method to work, I have to incorporate both equations. And the reason why I need a method is because I need to be able to solve for the variables one at a time. And this allows me to do that. Okay, so let's label these number 1 and number 2. Can you pick out the variable that looks the easiest to solve for? Definitely any variable that doesn't have a coefficient or a number in front. That's going to be the easiest. That doesn't mean that you couldn't pick any of these others, but if I pick this one, I for sure won't have any fractions to deal with. So I'm going to go for that one. All right, so we're going to solve for y in equation number 1. Okay, so here is equation number 1. I want to get y by itself, so I'm going to move my 2x over to the other side. Notice I still have this negative here in front of the y. I haven't gotten rid of that yet. I'm so used to putting the x term in the front. I'm going to go ahead and do that, but you really don't have to do that right now. We're not talking about equations of lines. In this method, we're not going to graph them or anything like that. So 2 minus 2x would be totally fine. This is just sort of my habit now. Okay, and now I want to get rid of this negative, so you can either multiply by a -1 or divide by, look at this as a -1. Either way, it's going to change the sign of everything. So I'm going to end up with 2x minus 2. Okay, now that I've done that, that's sort of the first step. Now I want to incorporate the equation I haven't used yet, and I want to substitute for y in this second equation. So let's do that. I'm going to substitute for y in equation number 2. So I have 3x plus 2, but I'm going to take out the y and put in this 2x minus 2 in place of the y. Because they're equal to each other, I'm allowed to do that. Okay, so just a quick pause, right? The whole point of doing this is to get down to the place where I just have one variable. Because I can't solve for two variables at the same time, this is one way to kind of move the y's out of the way, and now I can solve with only x's. That's sort of the motivation behind it. Okay, so now I have just one variable, so I can use what I've been practicing to solve for x. So we've got 7x. Can I go ahead and add this 4? So that's going to give me 7x equals 14. And I can divide by 7. So it looks like I get an x value of 2. All right, keep in mind that I need both an x value and a y value as my final answer. So I want to take this x value. I have 3 options. I can go back to equation number 1, equation number 2, or with substitution, I have this great place to go back to that's really direct, and I'll get, usually it's fastest. If I do a different method, I don't always have that, but this time I do. So I'm going to go back and plug in 2 for my x and calculate my y. Whole lot of 2's in this problem. Okay, so it looks like I get both x is 2 and y is 2. So you're welcome to leave them separate, but if you want to, you can list your solution as a point, since that's kind of what's going on here, right? These are 2 lines, and the point where they crossed was 2, 2. Okay, so that is the substitution method. And I think it's usually the best if you have a variable like this one that doesn't have a number in front. Right? That's a good time to use substitution. The other method we have at our disposal is called the elimination method. So this one's a little bit harder to put into words. That's why it looks so wordy right here, but once I show you how it works, it's usually not as daunting as these words look. So the idea is that we're going to eliminate a variable which allows us to solve, we'll say allows us to solve for the variables one by one. Okay, so in order to eliminate a variable, the coefficients or the numbers in front of that variable must be additive inverses or equal and opposite, right? So for example, we're hoping to get, say, 5x and negative 5x, right? Equal but opposite numbers in front, so that when we add them together, they add to 0. So to make that happen, this maybe is not a good example to show you the second part, but that's okay. To make that happen, we're going to multiply either one or both equations by a number to set this up. Okay, and so once we have that scenario, if I make them equal and opposite, I'm going to add the equations. Let's just leave that there. If I made them equal, then I'd want to subtract, right? But the goal is to get a 0x or eliminate one of those variables. And just like with the last method, I can choose which variable I'd like to eliminate. I can kind of look at it and see which one looks easier. But I can really eliminate either variable for any problem. So the question is, which variable would you like to eliminate? Why don't we eliminate x? Okay, so to eliminate x, what do I need to multiply by to get the numbers in front of the x's to be equal but opposite? They're already opposite. One of them is negative and one of them is positive. But I'd really like them to be 4x and negative 4x. So I can do that if I multiply the second equation by 2. Okay, so what I'm going to do is I'm going to copy down the first equation. And then I'm going to multiply everything in the second equation by 2. Not just the x part, but all 3 parts. So that's going to give me negative 4x. 5y times 2 would be plus 10y. 29 times 2 would be 58, I think. Okay. And then I'm going to add these two equations together. So the 4x and the negative 4x make 0x, which adds to 0. Negative 1y plus 10y will be 9y. And negative 4 plus 58 will be 54. So if I divide by 9, oops. Okay, notice by eliminating the x's, that allowed me to solve for just the one variable y. And then, now that I have y, I can go back and find x to go with. So this is another way to solve for the variables one at a time. Okay, so I don't have the nice handy place that substitution offers, so I need to go back to one of the original equations. It doesn't matter which one because this is the point that they share, so I should be able to use either one and get the same answer. I'm just going to use number 1. So I'm going to solve for x using equation number 1, not for any good reason. I just have to pick one. So I'll have 4x minus 6 equals negative 4. And I want to know what x is, so I'm going to solve. Okay, and I end up with 2 divided by 4, but I can reduce that to 1/2. So again, you're welcome to leave your answer as 2 separate spots here, or you can write it together as a point, 1/2, 6. All right, so both of these examples have given us a value for x and for y, which means we have that intersecting lines scenario. So let's do one more that is not the intersecting lines scenario, so you can kind of see what that would look like. This one's also from your book. Why don't we try and practice the elimination method one more time? You could use either method, and I'm never going to require you to use one above the other. You can choose whichever you like. But just for fun, let's try to use the elimination method. And let's say we want to eliminate x again. So to get rid of the x's, I need the numbers in front to be equal but opposite. So what do I need to multiply by? So I'm looking for a number sort of as my goal. That's a least common multiple, right, of 2 and 3. I mean, it doesn't have to be the least, but that would make my number smaller, right? So the smallest number I can think of, bigger than 2 and 3, that 2 divides evenly into and 3 divides evenly into, would be 6x and negative 6x. Right, so my goal is to get that set up. So I can do that if I multiply equation number 1 by 3, and if I multiply equation number 2 by 2. So remember, when I do that, I have to multiply the whole equation, not just the first number. So that's going to give me 6x minus 12y equals 12. And then I'm going to multiply the second equation by 2, so that's going to give me negative 6x plus 12y equals negative 12. Okay, and this is usually the point where you may recognize, hey, something weird is going on here, right? So I set out to eliminate x, but I am actually going to end up eliminating x and y. And this time I'm even going to eliminate the constants. Okay, so what do I get? I get 0x plus 0y equals 0. Well, it doesn't matter what x and y are. This is just 0 plus 0. So I get 0 equals 0. Okay, so if this happens, if your variables drop out, and it can happen with both elimination or substitution, then you want to look at what's left, right? Do I have a true statement or do I have a false statement? In this case, we have a true statement. So if it's true, then that is the case where we have overlapping lines. And we're going to say our answer is that we have infinitely many solutions. Okay, now I want to say a couple more things about that. First of all, let me say that there is a more complicated way that you can represent the points on these overlapping lines, right? So besides writing this as our answer, we could go into more detail. I'm not going to ask you to do that in my class, but you could. Okay, so if you pull up extra problems from the textbook, you might see that, and just know that that's a way to represent this. Okay, because our lines are overlapping, that means that these two equations, when I graph them, I get the same line. Okay, and now that we look back at the equations, maybe you could see usually one is a multiple of the other. So this one's a little harder to see. I tried to pick one that wasn't too obvious, but if I multiply by 1.5, right? 1.5 times 2 is going to give me 3. 1.5 times 4 is going to give me 6, right? Or I guess it would be negative 1.5, right? So these are a multiple of one another. I am not a kind of person that would have spotted that at the beginning. I would have spotted it here when I started to cancel some weird stuff out, okay? But maybe you could spot that from the beginning. All right. Okay, so this is the overlapping lines scenario. I'm not going to do a separate example, but let me just demonstrate sort of what it would look like if you had the parallel line scenario, right? So maybe we did something similar to solve. But instead of getting 0 equals 0, we got 0 equals 5, right? So then we look to see, all right, is this true or false? This is definitely false. If it's false, that means we have parallel lines. And we don't have a solution in that case. Okay, so when we work an example like this out, right, the method is still the same, but it's going to depend on, did I get something true or false at the end? If I got something true, it's overlapping lines. If I got something false, it's parallel lines, and I have no solution. All right, well, I hope that gave you a really good summary of how to solve a system of equations. Like we said at the very beginning, this is one of those things that we do in our class, and then we really dive in. If you keep going to pre-calculus, depending on your major, you get to do 3 equations with 3 variables and build a matrix, and there's lots more to this story. So this is just kind of the first step. All right, well, good luck with this, and we'll see you in the next video.